Hello, everyone. My name is Enrico Bonilauri. I'm the Chief Product Officer of Immune Systems. What we do is teach builders in North America how to implement passive house cost effectively in different climate zones. The US and North America ranges from Florida, which is very hot and humid, all the way to Alaska, that is very cold and dry. So we need to educate professionals on how to implement the principles of passive house effectively in different climate zones in a way that is cost effective, safe, and that will deliver very good and efficient buildings that meet the passive house standard. So the presentation I'm giving you today is called Climate Specificity of Building Component Design and Passive House Requirements. So climate specificity is very important for any building design, and specifically for passive house and the success of these projects. Passive house is a very advanced performance-based standard for building quality with specific goals that deliver healthy buildings through high hygiene, very high thermal comfort. The buildings end up being very durable over time. And with that, you have very high energy efficiency. And the key to that is also to optimize all of the above in order to have very cost efficiency in the project. So the hygiene and comfort requirements are part of the backbone of the passive house standard. Too often we see very poorly built buildings that are very uncomfortable in terms of temperature, as well as very poor management of moisture, resulting in condensation and mold. Part of the passive house standard is to have the hygiene criterion and the comfort criterion that are optimized by climate in order to avoid these issues by design. So you get rid of condensation and mold via the hygiene criterion, and you have very high thermal comfort thanks to the comfort criterion of the passive house standard. This is climate specific. We have here a map of Spain highlighting different locations that we looked at for the development of this presentation. And the color of those arrows actually matches the climate zoning issued by the Passive House Institute. We see in Spain, we have climate zones ranging from hot to warm temperate. And in the map of Europe, we see also Frankfurt that we kept just because that's where the passive house standard came from. That is the cool temperate climate. Looking at North America, we have chosen two locations. One is Denver, the little blue arrow, that is where I'm presenting from. And the yellow arrow is Bainbridge, Georgia. Two very different climate zones and two very different approaches to deliver the same passive house standard. The climate zones issued by PHI are actually based on heating degree hours as well as solar radiation, and other institutions such as ASHRAE base their climate zoning on a different set of parameters that include heating degree hours and cooling degree hours. There is some correspondence between the two, but it's important to understand that the way you label a climate may vary depending on the institution that is applying this label. For this presentation, we looked at different locations and the related climate. We have here a number of cities, mostly in Europe and a couple in the US, and they are ordered by latitude. So at the top, we have the northernmost locations, and at the bottom, we have the southernmost location. These are, we list here the PHI climate, but we also list a number of metrics for the climate because those are important to understand the differences that you may have within the same climate zone. So we have two locations that are located in the cool temperate climate. One is Frankfurt, Germany, and one is Denver, Colorado. And they have similar degree hours, but you see Frankfurt is cold because of its latitude. It's quite north. Whereas Denver, it's cold because of its elevation. We are at 1,600 meters above sea level. So one fundamental difference between these two climates, although the heating degree hours are about the same. We have 93 kilokelvin hour a year in Frankfurt and 94 in Denver, but we have a substantial difference in solar radiation. We have 3 times as much solar radiation in Denver than we have in Frankfurt. So designing a passive house building is considerably easier in Denver than it is in Germany. Looking at warm climate zones, I picked Bainbridge, Georgia, because we have a project going on down there. And we are comparing here to Seville in Spain. And just looking at the temperatures, Seville is actually warmer than Bainbridge. In fact, Seville is listed in PHPP, where this climate data comes from, as a hot climate, whereas Bainbridge is warm. Another important factor in the Bainbridge climate is that the solar radiation is not very high, probably because it's very hazy in the summertime. However, it is very humid. Georgia is a swamp, very close to Florida. So in trying to design a very good and efficient passive house building, you do need to factor in these specificities of the climate. Looking at the psychometric chart, those differences between Seville and Bainbridge become more evident. We have the target summer comfort point at 25 degrees Celsius and 50% relative humidity. And Seville is actually not too far away from that in terms of you will need to have some sensible cooling, but not too much dehumidification. Whereas Bainbridge is considerably more humid, and so you need to work out harder in order to meet that comfort target. The sensible cooling is fairly similar for both, but for Bainbridge, you have a considerably higher need for latent cooling that is dehumidification. So in this, you can see how you need to develop a strategy for your building and for your building components in order to meet these climate-specific requirements. So this is a project we have going on. It is 4 buildings of 14 apartments each, 2-story, fairly simple and straightforward design, and they want to meet passive house certification. And you can see that while the heating demand for passive is capped at 15 kilowatt hour per square meter a year, the cooling and dehumidification demand is actually climate specific. The dehumidification component is climate specific. So if the hardest thing to meet in Denver to meet passive house is the heating demand, in Bainbridge, Georgia, the most challenging part is actually the dehumidification. It's actually, you need to work on the design side to meet that because it's difficult. Looking at the way the passive house building envelope is typically developed, by climate zone, you have certain U values that you're typically working with, different approaches to avoiding thermal bridging, type of glass, triple pane glass, or warm edge spacer. And all of these components do provide value to different parameters of the project. All of them pretty much contribute to reducing the need for heating as well as reducing the need for sensible cooling. If you're looking at the hygiene requirement, avoiding thermal bridges and having good glass spacer allows you to have high enough FRSI values for you to avoid mold condensation, thus meeting the hygiene criteria. The comfort criterion is met by having a combination of glass spacer, frame quality, and window installation that does meet the comfort requirement. One thing that the envelope does not really help with is passive dehumidification. That does not really exist. So in trying to meet the dehumidification need for Bainbridge, we had to do some trade-offs for the project. So in trying to do that, our goal was to reduce the amount of cooling or sensible cooling as much as we could, so we could free up some space for latent cooling in the passive house balance. And we did model a number of scenarios. The graph on the left shows a combination of heating demand and that is represented by the orange columns, and cooling in terms of sensible and latent cooling that is represented by the blue columns. And we modeled that at different incremental steps of thickness of this insulation under the floor concrete slab. So we did 0 centimeters, 2 centimeters, like all the way up in incremental step to see how much this impacted the heating demand as well as the cooling demand of the building. And the side effect is that the more you reduce the insulation under the slab, the more you couple your building with the ground, the less the cooling becomes. And you do have, as a trade-off, more need for heating. However, the sum of the two, we were looking at the total balance, heating and sensible plus latent cooling, and the sum of the two resulted being at the lowest with no insulation under the floor slab. So in this case, we decided not to have any insulation under the floor slab of the building. It's important that when you do this process to have all parameters in mind so that you don't forget something. In this case, hey, I'm removing the insulation from under the floor slab, I may have condensation. Now, because Bainbridge is so humid, we're already planning on having active dehumidification separate from the sensible cooling anyway. So this construction has a mini split system for the sensible cooling and additional dehumidifiers for the latent cooling. So we had a very good understanding of the humidity level inside the building. And via the temperature factor FRSI, we made sure that we didn't have any issues with condensation on the floor. So we modeled also the temperature factor at the slab for the incremental step of insulation. And in reality, even if we did not have any insulation under the floor, we ended up having no issue with condensation. There are ways to assess internal conditions inside the building. These two graphs show the design conditions over a year for temperature and relative humidity inside the building, depending on climate, type of occupancy, type of mechanical systems, including heating, cooling, and dehumidification, as well as mechanical ventilation. And what we're looking at in this graph is the green line that represents the relative humidity inside the building, which is very important if you want to have a durable and healthy building in any climate. So looking at these different seasons, you can see that an issue we have in Denver on the left side is that in wintertime, it is very dry, with the internal relative humidity being around 20 to 30%, which is very dry and becomes uncomfortable. Whereas in Bainbridge, on the right-hand side, we have very high humidity year-round. And that was one of the reasons why we ended up having an active dehumidification system that is decoupled from the ventilation system and is decoupled from the sensible system. So in doing this kind of analysis, you also want to make sure that you're looking at advanced building science. We have at the top here a typical wall section for a timber frame wall for passive house in Denver, Colorado. And you have an air barrier that is internal on the warm side to avoid condensation. Whereas at the bottom you see the wall section for a passive house building in Georgia, you see less insulation because it's warmer, so you do need to have less insulation. But also the air barrier, it's important to have an air barrier for air tightness, but the position of the air barrier relative to the thermal insulation is less important than in cold climates. In warm climates, you can get away with your air barrier being located also on the outside if needed, because the external temperature is not very cold, so that will not cause any convection to condensate. So in this approach, you need to really make sure that your approach to physics and to building science is up to speed with the most innovative method. If you look at the wall at the bottom of the slide for Bainbridge, and if you did a dew point method calculation, that is the Glaser method, you would fail the test. And that would be, if the test that is failing is not the wall that is failing, you would not have condensation in this wall. But the method, the Glaser method that was developed in 1938, is obsolete and oversimplified. So it does not account to too many factors. So this wall would fail, whereas in reality it does not. And in looking at more advanced building science, you see that even if we consider 10 consecutive years and we consider infiltration from rain and exfiltration of air from the inside to the outside, the building does not accumulate water over time. The relative humidity, that is the green wiggly line, never meets condensation. This little graph shows the mold index according to ASHRAE standard 160, which mold does not develop inside the assembly. And finally, the wood panel OSB sheeting does not meet high moisture content that would cause the wood to rot. So all of these parameters show that with advanced building science, you can have better optimized building construction than you would have with older design methods, such as the Glaser method. And in developing that, we have here a detail that is developed for Denver, Colorado, at the junction between the insulated floor slab with concrete. You see, this is the external junction between the floor slab and the external wall. And you see there is insulation under the slab about 20 centimeters, and you do have about 33 centimeters of insulation in the walls. And you do need to have thermobreaks to avoid thermobridging and so to avoid molding condensation. So this junction is designed for a cold climate. For a warm climate, the same junction will look very different in that you do have insulation in the walls, but you have 18 centimeters and not 33. And you have no insulation under the floor slab, which saves a lot of money and actually improves the whole building performance in terms of heating and cooling. At the same time, you do not have thermobreak between the internal floor slab and the foundation wall because you don't need it. It's very important for you to understand what you actually need in passive house so that you can make your building optimized both for energy performance, cost, and health. That being said, to recap, in order to have climate-specific design, you really want to know the rules of the games. Rules of the games being building physics. The graphs on the side recap the parameters we typically look at in passive house construction, and at the bottom right-hand side, you see the recap of the heating and cooling for the Bainbridge project. So passive house is a performance-based standard for building quality. It's not a religion. It's very important for you to understand what you actually need and what you don't. The requirements, including the hygiene criterion, the comfort criterion, and all of that, are climate-specific, and they are based on clear goals for hygiene, comfort, durability, and energy and cost efficiency. And it's key for you to understand these goals for optimize the design for the local climate. It's very important for you to understand what you do need and what you don't need. What you don't need, you can avoid, and you can save money and time. That being said, I thank you for the attention, and I'm happy to answer any questions. Thank you.